Hey everyone, welcome back to another video by Camroom 5. In today's video, we're going to be talking about the theory behind the formation of colored complexes. So before we talk about that, we need to revise that there are three different axes that our d orbitals are spread onto. We have the YZ plane, where the dyz orbital and their four lobes are present. Then we have the green one, which is the XY plane, where the orbitals of the dxy are present, the four lobes of that orbital are present. Then we have the yellow one, which is the dxz plane present between the x and z axis, xz plane, where the orbitals of dxz are present. These are the four lobes of dyz, xz, and dxy. The other two orbitals, which are more concerning for us here, are the four lobes of the dx square y square and the dz square, along with obviously the donut present on the dz square. Why these orbitals are important? Because these orbitals are present on the axis. And in octahedral complex, the ligands are coming from on the axis, not below or between the axis. So in octahedral complex, all the six ligands and their lone pairs come from all six axes, x, y, z. And that is why when they come in, the d orbitals face different repulsion. So in a typical octahedral complex, you can see the two orbitals and the three orbitals get split into two sets. There's a lower energy orbitals, which are the ones between the axes, and then there are two orbitals which are higher energy orbitals. These are the ones which were on the axis. So this is the phenomena of orbital splitting, or you can say d subshell splitting. Which orbitals go for the lower energy? It is the between the axis orbitals like dxy, dyz, and dxz, also known as the T2g orbitals. The ones which were on the axis were the dx square y square and the dz square, also known as the EG orbitals. They go for higher energy because obviously they face more repulsion because the lone pairs are coming from that direction only. Tetrahedral complex shows the exact opposite, because in the tetrahedral formation, the ligands are coming from between the axes. So dx square y square and dz square go for lower energy, while dxy, dyz, and dxz, also known as the T2g orbitals, go for higher energy. Between these two energy levels, there is a delta E, and this delta E energy difference corresponds to one of the photons in the visible light region. And when an electron from the lower energy orbital absorbs a photon from the visible light region, it jumps, it excites to a higher energy level. So a photon is absorbed, and this energy is absorbed for the electron so that it can jump from lower level or lower energy level d orbitals to a higher energy level d orbital. And the remaining photons are reflected, which impart color. Now we're going to connect the idea of color with another concept of transition metals known as the ligand exchange reaction. It is like the name implies, when one ligand substitutes another ligand on basis of higher stability, or you can say K step. It is a concept that we're going to talk about in the next video. Imagine you have a cobalt 2 salt where cobalt has a +2 oxidation state. You dissolve it in water to get a cobalt complex where water is the ligand. It has a pink color. But when you add few drops of aqueous ammonia, it forms precipitates of copper 2 hydroxide. Upon adding excess ammonia, you get the brown colored solution where ammonia has substituted water as the ligand, and now the complex contains 6 amino ligands. In a very similar reaction, now if you add concentrated hydrochloric acid, you get a dark blue solution because now the chloride ligand replaces the water ligand. And if you add excess water in the chloride complex, you return to the water as the ligand complex, which means it's a reversible reaction. So if you write the equation of this, if the cobalt hexa aquo complex is there and you're adding concentrated HCl, through a reversible reaction you get the tetrachlorocobalt complex, which has the dark blue color, and the water as the ligand has been replaced. The chloride ligand here replaces the water ligand, and that is why we call it a ligand exchange reaction. This is a reversible reaction, and we can even write the Kc expression for it. For any ligand exchange, that would be called as the K-stab expression. We'll talk about in the next video. So water addition, like if you add more water here in the complex, you reverse the direction of the equilibrium. Equilibrium shifts to the left and you go back to the original pink color. Similarly, for copper complex, which is a blue solution, if you add concentrated HCl, you get a tetrachlorocopper complex, which has a green solution. If you add excess water, you go back to the blue solution, which means it is a reversible reaction. Writing the equation, we can see that in the aquo copper complex, if you add concentrated chloride ions, you get the tetrachlorocopper complex, and water has been replaced by the chloride ligands. Upon addition of few drops of ammonia, you get the blue precipitates of copper 2 hydroxide, and upon excess ammonia, ammonia replaces as the ligand to make a dark blue solution. Here in the copper 2 hydroxide, adding excess ammonia means ammonia is going to work as the ligand. So NH3, 4 ligands of the NH3 replace, and then you get a dark blue copper complex, which has the color that you see in the testing. Now this question is very clear about explain why chromium complexes are colored, so let's write it. It says when complexes are made, the D subshell splits into lower energy and higher energy d orbitals. That is the first argument that we talked about in the video. There is a delta E gap between these orbitals, the lower energy and the higher energy d orbitals. An unpaired electron absorbs a photon from visible spectra, or you can say from visible light, and is excited to higher energy level. The remaining photons, like we talked about it already, the remaining photons and the remaining wavelengths reflected back impart the color that you see. So that is enough for 4 marks. You need to talk about the keywords here. So your keyword should be the D subshell splits, lower energy, higher energy, the idea of delta A, the idea of absorbing a photon, and then obviously reflecting it. 4 different compounds can be obtained when anhydrous chromium 3 chloride reacts with water under various conditions. So just look at the table first, and you're reacting with silver nitrate to form precipitate. Now this concept is very important for us. You can see that in each formula of the compound, there are so many chloride and so many water ligands. When you precipitate something, it means that it's not a part of the complex, because complex will never allow the ligand to precipitate. If 3 mole of AgCl can be precipitated, which means that the 3 chlorides are never part of the complex. They are just spectator ions. It means the formula of the complex is 6 water ligands and all three chlorides are not part of the complex, they are outside the complex. So the complex has water ligand, but the three chloride are in the ionic bonding, they are just as spectator ions. So remember, only precipitation can be happened if the ions are outside the complex. Similarly, if you are precipitating 2 chloride ions, it means that there are 5 water ligands, 1 chloride ligand, and the other 2 chloride are just doing ionic bonding. The other 2 chloride are just outside the square bracket because they are not part of the complex. If you are making 1 chloride precipitate, it means that there are 4 water ligands, 2 chloride ligands, but there are 2 chlorides which are not part, 1 chloride which is not part of the complex, that is why it can precipitate. So draw 3D structures, and in order to draw the 3D structure, I will draw the general octahedral geometry. In the complex P, you can see that there are all water ligands. So you will draw just oxygen atoms as the coordinate bond lone pair donor and the H2s around it, and then you put the square bracket and then you place the charge on it. Let me draw the square bracket correctly. A square bracket and then the charge. Charge was 3 plus because 3 chlorides were outside the square bracket, which means the complex was 3 plus. To draw structure Q, there is 5 water ligands and there is 1 chloride ligand. Overall, then you place the square bracket and then you place the charge on it. Remember the fact, 2 chlorides outside means there's a 2 plus charge on the complex, and the 2 chlorides are just doing ionic bonding, which can be later precipitated. When you talk about R and S, you need to understand that there are 2 chlorides in the complex. So you can place them together or opposite. If you place them in a similar direction like this in the structure R, they will create a net dipole. So the overall complex is going to be polar because the net dipoles can't cancel each other. But in the structure R, let's show the dipole, and let's talk about structure S. In structure S, when you talk about the complex formation, you can notice that the table has called it non-polar, which means both chlorides are oppositely placed. Opposite placement means the dipoles cancel each other. And when you place the square brackets, you will realize that it has a symmetrical structure. Suggest why complex ion S is nonpolar. So my answer is going to be simple, as both dipoles from chloride ligands cancel each other. Define the term bidentate ligand. It's a very simple idea. It's a ligand that donates two lone pairs to make coordinate bond with the transition metal ion. Coordinate bond with the metal ion, transition metal ion, same thing. They want you to draw the structure of Z. Z is the conjugate base. Z is the conjugate base of picolinolic acid, something like that. Oh no. So just to draw the conjugate base, you remove the proton from the carboxylic acid group and you place a negative charge. Remember, the nitrogen atom and the oxygen atom have lone pairs, so they can act as ligands. Z reacts with aqueous chromium ions in the 3:1 ratio, where 3 is the bidentate ligand. 3 times bidentate means 6 lone pairs. So 6 lone pair means that my chromium ion is accepting 6 lone pairs. So coordination number 6 and geometry is octahedral. Now, part D says the diammonium chromium oxide decomposes readily on heating to form chromium oxide, steam, and inert gas. Deduce the oxidation number. Now that is pretty basic. Ammonium is twice, there are 2 chromiums and 6 oxygen, which means net charge is 0. Ammonium is +1, chromium is unknown, and 7 oxygen means minus 14 oxidation number. You solve for X, you get +6, and Cr2O3 is obviously +6. Writing the final equation, we see construct an equation. So basically, my ammonium chromium oxide decomposes to form Cr2O3, inert gas, which means obviously nitrogen because there's no gas as inert as nitrogen, and the remaining thing can be seen as obviously H's and O's, so I receive water vapors. I hope these ideas are clear to you guys. I would recommend looking at their working again and reach out if you have any concerns. Stay tuned, guys.